The Gram-Schmidt process can be generalized to any subspace in any dimension Rn. And this is generally called the Gram-Schmidt orthogonalization process, because what you're doing is you're taking some basis that isn't orthogonal and you convert it into an orthogonal basis for that subspace. So I'm just going to walk you through something. The picture that I will draw here will obviously be a picture in R3, but the process generalizes. So here's the first step of the process. You're going to take any one of your vectors in this basis and call it the first orthogonal vector. So just for simplicity, I'm going to say that the first orthogonal vector is just v1. So in my picture here, I've got v1 illustrated. I'm going to let w1, capital, be the span of that v1. Or in my case, the span of this w1. It's the line that I get spanning that v1 spans. So what I'm then going to do is then I'm going to project the second basis vector. Any one of them will do. That'll be fine. We're going to project this v2 onto that subspace w1. Now, the idea here is that any two independent vectors, like you have in a basis, will always span a plane. So you'll always be able to draw a picture like this. You're going to project it down. You'll get v2 with the hat. So find this v2 with the hat. It's just going to be v2 dotted with w1, w1 dotted with itself into w1. And the real important point here is that you'll now get v2 perpendicular, and v2 perpendicular is just going to be w2. You're going to call that the second vector, the second orthogonal vector. So then you're going to let w2 be v2 perpendicular, which is just going to be v2 minus v2 hat. And that's going to give you a v2 subtract v2 dotted with w1, w1 dotted with itself. And so now you have created a orthogonal basis for that subspace. So w2 is going to be the span of w1 and w2. So it's basically that plane that you see in the picture. And note that this is the same as the span of your original two vectors that you chose. That's kind of the whole point. All you're doing is just switching the language you want to use to describe all the vectors in that plane. Once we get to here, then the idea goes further. We now have some third vector, and that third vector will live off of that plane. We'll say that that's v3. We are going to project that third vector down onto the plane and get some v3 hat, and then we will end up repeating this process. Once we get the v3 hat, we'll get this v3 perpendicular, which we are going to call w3, and the process goes from there. So the idea now is that we are going to let, sorry, I may put a vector sign here when I shouldn't have. What we're going to do is we're going to take our v3 and project it onto w2, which is the span of those two vectors, w1 and w2. And as before, v3 hat is just going to be represented by these Fourier coefficients. We're going to take v3 dotted with w1, w1 dotted with w1, times w1 plus v3 dotted with w2, w2 dotted with w2 into there. And then we are going to define the third orthogonal vector as v3 perpendicular is v3 minus v3 hat is v3 minus this stuff that we just wrote down. v3 dotted with w1, w1 dotted with itself, so on and so forth. And you can see that this process can just extend to as many dimensions as you'd like. Right? You can generalize this to n dimensions. And what you'll do is you'll keep taking a single vector, projecting the next one onto the subspace, creating an orthogonal basis, taking the next vector, projecting it onto that subspace, and you're taking successively larger dimension subspaces and projecting onto each one of those. And so when you generalize this all together, what you're going to find is that the general nth vector is just going to be Vn minus Vn hat. And it's going to be a big mess, but you'll understand where the formula is coming from. Vn dotted with W1. And this is perfect for an algorithm. Those of you who are a little bit more comp sci inclined will start to have the gears turn in your head, and you say, oh, this is just a set of steps that I can code or program and have a computer do this in general. And so what we end up getting is an orthogonal basis for my W, and it's W1 up to Wn. If I normalize it, I will get what's called an orthonormal basis for W. And we will call them U for unit vectors. All we would do is just take each one of those W's and divide it by its length. So I would like to show you an example of all of this, right? So here's an example where we can use this orthogonalization process to come up with an orthogonal basis. So I'm going to give you a matrix, and the issue here, or the problem that I'm going to be interested in, is I'm going to say, look, let's let W be the column space of this matrix, and I would like to find an orthonormal basis for the column space of A, which is my subspace W. Now note, I've got three vectors, A1, A2, A3, and each one of them have 4 components, so this thing lives in 4-dimensional space. Now also note that I could take this matrix A, and if I do a bunch of steps, I'm hoping that you can see that I'll be able to row reduce this matrix. So you can pause the video if you'd like, and you can show that if you were to row reduce this matrix, you would end up with something like this. And you would see that there are 3 pivots. So the pivot columns of a matrix form the basis for its column space. So that means that the dimension of this column space, or the dimension of my subspace W, is 3. And that means that a basis for the column space of A is just going to be formed by those 3 columns. But it's not orthogonal. Right? Those columns, you can take the dot product of any of them and you'll see that they don't give you 0. Okay, so now we're going to start the Gram-Schmidt orthogonalization. We're going to let the first column vector be W1. And so that means it's going to be -1, 3, 1, 1. That vector spans a line. So we'll say that the first subspace is just going to be the span of this W1. It's just some line in R4. What I then want to do is I then want to project the second column onto this line. So in terms of a picture, here is W1. It spans some kind of line. There's A2. I'm going to project it down. There's A2 hat. And the vector that I want is A2 perpendicular. So the idea now is that A2 is just going to be A2 dot W1, W1 dotted with W1 into W1. A2 perpendicular is going to be A2 minus A2 hat. If you were to do these dot products, you can calculate things here. What you'll find is that you'll get an A2 subtract 4, my mistake, minus 36 over 12 times W1. So if you actually sit there and calculate those dot products, you're going to have to pause the video and go back and calculate things there. You'll get an A2 plus 3W1. Calculating this, you will end up finding that your second vector will be 3, 1, 1, negative 1. So this is what we are going to call W2. Now you can check that W1 dotted with W2 is going to be negative 1, 3, 1, 1 dotted with 3, 1, 1, negative 1. It is in fact going to give me a 0. So that's great. So in this particular case, if I were to compute A2 dotted with A1, I'd get a negative 36. W1 dotted with itself, I'll get that. So that's great. Those two now span a plane. So we are going to let W2 be the span of my new set of orthogonal vectors, W1 and W2. They are going to be a plane in R4. And I now want to project A3, the third vector in that column space, onto W2. And from there, I want to find A3 perpendicular. So in terms of a picture, let me draw it below here. So in terms of a picture, what I've got is this. This is W2. I've got orthogonal vector 1, W1, orthogonal vector W2, and now I've got some third vector up here, the third column. I want to project it down onto that subspace, A3 with the hat, and from there I want to do some vector subtraction to find A3 perpendicular. Now remember, the point here is that the span of my original two columns is going to be equal to the span of my new orthogonal vectors, W1 and W2. They span the same space, you're just using two different vectors to do it. W3 is going to be A3 perpendicular, it's going to be A3 minus A3 hat. A3 is going to be given just by the column entries 6, 3, 6, negative 3. A3 hat's a little bit more messy. This is going to be A3 dotted with W1, W1 dotted with itself into W1 plus A3 dot W2, W2 dotted with itself, W2. You can pause the video, you can take a look at those columns, should have written them down. What you would find is that this is going to end up giving you the following. It's going to be 1/2 of W1. That's the first Fourier coefficient is a 1/2. And the second one is going to give you 5/2 W2. So again, take the moment to pause that out, compute those. And when you sit there and you plug all these numbers in, what you'll find is you'll get a vector that looks like this. And you do the calculation, you'll get this third vector. So W3 is now -1, -1, 3, -1. And you now have an orthogonal basis. You can always check that your original three vectors are perpendicular to this new one, which they are. And so you now have an orthogonal basis for the column space of A It's those three vectors that you came up with at the beginning. -1, 3, 1, 1. The second vector you found, 3, 1, 1, -1. And the third one you just computed, -1, -1, 3, -1. They are not unit length. So if you wanted an orthonormal basis, what you would find is that you need all of the lengths. So the length of all of these vectors turns out to be the same, turns out to be root 12. And so if you sit there and you compute them, they will all have the same length of root 12. So the orthonormal basis, u1, u2, u3, is basically just 1 over root 12 w1, 1 over root 12 w2, 1 over root 12 w3. Now, unfortunately, when you do this normalization, you're always going to get these weird square roots. Unless the question is doctored, you're always going to end up getting yucky, weird roots. Now, why would you care about this? Why would you want to bother with an orthonormal basis? Orthonormal bases are nice. Whenever you have one of those, there are these nice properties of length. It doesn't change lengths when you work with them, and that's why people really want to bother. There's another idea coming up that will also take advantage of that orthonormality.